Okay, so we're going to go over significance tests for a difference in means. We're going to go through an example problem here that I'm going to work through, and then we're going to go through another example through the book problem, and hopefully that'll wrap up all your big ideas and you get a better understanding for a test for the difference in means. So according to a Stanford Business article, Americans may eat fewer calories at restaurants if the calories of the food items are labeled on the menu. To investigate this, researchers compared Starbucks receipts from locations where the menus were labeled to receipts from stores where the menus were not labeled. A random sample of 30 receipts from stores with the menus labeled had an average number of calories of 225 calories with a standard deviation of 100 calories. A random sample of 40 receipts from stores without menus labeled showed an average of 265 calories per receipt with a standard deviation of 75 calories. Does this provide convincing evidence that the average calories per receipt at Starbucks with a labeled menu is less than at a Starbucks without labeled menus? Okay. So again, the question, does this provide convincing evidence that the average calories per receipt at Starbucks with labeled menus is less than at a Starbucks without labeled menus? So right there, the last little sentence tells you what our null and our alternative hypothesis is to begin with. Well, let's start out with parameter here. Again, talking about what they're wanting to look at, right? They're wanting the difference here. So in which case, we're going to look at this between our mu1 minus our mu2 is going to be the true difference in mean calorie intake. All right, so the true difference in mean calorie intake. Okay, so then what were our hypotheses? Because we just said that, right? So we know that the null is going to be that they equal, right? Equals 0. So that the actual difference does not matter. So our null hypothesis is going to be that our mu1 minus our mu2, that difference, is going to be 0. They're going to be the same. There's not going to be any difference there. However, though, our alternative, what they're proposing in this, is that the Starbucks with a labeled menu is less than a Starbucks without a labeled menu. So in other words, our difference, our mu1 minus our mu2, is going to be less than 0. It told us that. It gave us less than right there, okay? So with this, let's look at significance level. So did it give us our significance level? It doesn't state it anywhere in the problem. And if that is unknown, if that is a question mark on what it is always going to be 0.05. Or you like to think of it as in percentage, 5%, right? Okay. With statistic, now we're looking at our x bar 1 minus our x bar 2. So in other words, the means from both of these and subtracting them to find the difference. Well, let's look at this. The store with receipts, menu labeled average number of calories, our average number, our mean, our average number of 225. So we got 225 for with receipts, and then without labels shows an average of 265. So 265, so 225 minus 265 is going to give us a negative 40. Okay, so right there off the bat, our difference, our statistical difference, is going to be negative 40. All right, so let's talk about our plan, right? Next step is plan. So for our plan, again, we have two samples, right? So we're doing one from store with receipts, one from store with one with labels and one without labels. So we're doing two samples. Now we're dealing with means, so that's a t interval, right? And again, we're talking about the difference in means. So thinking about what type of problem we're working here. Again, we're doing a 2 sample t-test for difference in means. Write it out just like that. 2 sample t-tests for mu1 minus mu2. Single explanation. Tells exactly what we need to do. Now our conditions. Again, our three conditions that we're always been checking for, right? In which case, with means, instead of large counts, to determine our approximate normal, we're going to use central limit theorem. So our first condition, as always, is going to be random. Is this random? Well, if we look back at the problem itself, it tells us random sample, right? Random sample. So random sample of 30, random sample of 40. So we've got random sample, right? So random sample, I'm just going to put 30 and 40. So we checked off random, boom. Now let's look at our 10% condition. As we've always been doing as well, a random for sure, and then our 10% condition, in which case we took a random sample of 30 for with receipts with labels. So we're going to say that's less than 1/10 of all receipts, right? Which I would think so, dealing with Starbucks. And then we're going to take 40 without label. And I would say that's less than 1/10 of all as well. Again, even if it's obvious like this, Starbucks, we know they sell millions of cups of coffee, so there's millions of receipts just from one area. Okay, so with that, even though it's obvious, write this out and put check mark. It is good that it checks off. I know that sounds kind of duh and obvious, but write it out. Again, act like the person grading doesn't understand anything you're talking about in the problem, and write it all out to where anybody from the street can come up and read this problem and understand where you're going with your numbers and why you went that way. So with this, now determine approximate normal for our sampling distribution. Again, because we're dealing with means, we're going to use a central limit theorem. So now it's not just one sample, right? We did two samples. So we're going to say 30 for one sample is greater than or equal to 30. So it checks off. And then we took 40. And that's greater than or equal to 30 as well. So both those check off. So our central limit theorem is good. We don't have to worry about drawing out any type of sample data as far as our numbers and making a dot plot or histogram or anything like that. These check off with being greater than or equal to 30, so we're all good. So that takes care of our plan. Again, you name the procedure and then you check off your three conditions. The do part. So for the do part, now we need to determine what we've got here and where we're going with this. First thing I like to do to start off with this is go through and find what our t-score value will be with that, right? So I'm just going to write this out. Again, we're looking for our t, taking our statistic, right? x1 bar minus x2 bar minus our null, all divided by our standard error of the difference, right? Which is the same thing as saying your standard deviation, but we're going to go ahead and just write standard error because I feel a few people are getting a little mixed up. So with that, again, it's the standard deviation of our sample. We're going to call it our standard error, and it'll help you make a little bit more sense of this. So with this, we already have our difference in means. We know that this is negative 40. We know that our null is 0 because our difference, we said right there, is 0. And then we need to determine our standard error. Well, our standard error is simply going to be, say, x1 bar minus x2 bar, standard error of those, of the difference. So it's the square root of standard deviation of our first sample, so with labels, so which was 100 calories. So we're going to come back here and say 100 squared divided by our sample size of 1, which was 30, plus the standard deviation of our second sample, which had no labels, and the standard deviation of that one was 75. So we're going to take 75 and square it, divided by 40. And we're going to do a little math there with that one, and I came up with 21.77 for that value. So with this, now we can find our t-score value right here. So we find that. So again, we got this is 21.77. So now if we were to write this out with our t-score, it's equal to negative 40 minus 0 all over 21.77. And we should get negative 1.84. Alright, and now we're going to go ahead and draw this out. Again, if you have this data, you want to draw this out and label your graph. So we're going to draw our little curve as best we can there. In which case we've got here now, we're going to say 0. We have our t-score of negative 1.84. Okay. And we're going to use this by saying I'm going to shade less than, because we said in our alternative hypothesis we're saying the difference is less than 0, so we're going to get from negative infinity up to our negative 1.84 t-score value. And again, this is labeled, in which case it's a t, and we're going to use a smaller number for our degrees freedom if we were to label this. So therefore the smaller sample size was 30 that we had, so we're going to say 30 minus 1 is 29. So we're going to say t29 for that one to set up there for the labeling of this guy. And in which case now that we have this, now we need to find our p-value. So for our p-value, we're going to take p-value. I'm just going to use the simple setup here of our one second. So we're going to take our TCDF. Well, not going to work here. TCDF. In which case we're going to take our lower bound as negative infinity. Label that lower bound. Your upper bound is negative 1.84 for upper bound. And our degrees freedom was 29. So use a smaller sample size to base your degrees freedom off of, in which case the smallest samples was 30. So as we label our graph over here, 29 for degrees freedom, we're going to use 29 for degrees freedom in our TCDF. And therefore we should get, well, let's look at that. So on the calculator, if you have a TI Inspire, and menu, 6, 5, and then 5 for TCDF. Lower bound, negative infinity, leave that number there is fine. I'm going to come here and let's say negative 1.84. And my degrees freedom is 29. I'm going to say OK. And I should get 0.038 for my p-value. 0.038. That's a horrible 3. Let me rewrite that. Okay. Now let's also look at the table as well to figure that out. So I'm looking at table D that I've listed in your notes here. We're going to look at this. So we know that we've got degrees freedom of 29. So we're going to look right here on 29. Okay. And we're going to come across here and see what value our t-star value looks at. We had negative 1.84. But we're going to have positive, really for positive 1.84 because we're looking for the upper tail. So we're going to say it's a positive 1.84 that we're looking for, okay? So let's look at 29, and 1.84 is going to fall between 1.699 and 2.045. And that corresponds to our p-value of 0.05 and 0.025. So if you're using table D, you can simply write that out by saying table D here says that is going to be the p-value is equivalent from 0.025 to 0.05, which is where our value fell, right? That we actually used the calculator for, 0.038. That's in between those two values. So either one of those will work because it helps you to determine your next step here. Alright, so we got our p-values. So now what we need to do, we need to conclude. In which case, what does this mean? If our p is low, we're going to reject the hoe. So if you have, in this case, I'm going to use the value we actually had here, 0.038. Say that's less than 0.05, which is our significance level, right? And therefore, we're going to reject the null. Alright, so now the last step we got to do here is just your conclusion. In which case, writing this out, assuming there is no difference in the average number of calories between the stores, there is a 0.038 probability of getting a difference of negative 40 calories or less purely by chance. And simply like I just wrote out there, 0.038 less than 0.05, and we reject the null hypothesis. So again, that's going through your state plan to conclude on how the process is worked out. So let's go through a book example real quick and see how this is worked out on a different stop problem and see if you got it all squared away.
Hey, this is Jason Molesky. In this example, we'll take a look at comparing two population means. Does increasing the amount of calcium in our diet reduce blood pressure? Examination of a large sample of people revealed a relationship between calcium intake and blood pressure. The relationship was strongest for black men. Such observational studies do not establish causation. Researchers therefore designed a randomized comparative experiment. The subjects were 21 healthy black men who volunteered to take part in the experiment. They were randomly assigned to two groups. 10 of the men received a calcium supplement for 12 weeks, while the control group of 11 men received a placebo pill that looked identical. The experiment was double-blind. The response variable is the decrease in systolic, the top number, blood pressure for a subject after 12 weeks in millimeters of mercury. An increase appears as a negative number. Here are the data. So for group 1, the calcium group, we can see decreases of 7 millimeters of mercury, increase of 4, decreases of 18, 17, and so on, and similar data for group 2, our placebo group. Now for this problem, we want to know if the data provide convincing evidence that a calcium supplement reduces blood pressure more than a placebo. We'll need to carry out an appropriate test to support our answer. Then we'll have to interpret the p-value in the context of this experiment. So let's follow our familiar four-step process, starting by stating our problem. We want to perform a test of the null hypothesis mu sub 1 minus mu sub 2 equals 0 against the alternative mu sub 1 minus mu sub 2 is greater than 0, or equivalently we want to test the hypotheses where the means are equal against the alternative mu 1 greater than mu 2. Where mu 1 is the true mean decrease in systolic blood pressure for healthy black men like the ones in this study who take a calcium supplement, and mu 2 is the true mean decrease in systolic blood pressure for healthy black men like the ones in this study who take a placebo. No significance level is specified, so we'll go ahead and use alpha equals 0.05. Well, we need to check our conditions. If they're met, we'll carry out a two-sample t-test for the difference of means. The 21 subjects in this case were randomly assigned to the two treatments, so our random condition is met. For a normal, large sample, we note that with such small sample sizes, we need to graph the data to see if it's reasonable to believe that the actual distributions of differences in the blood pressure when taking calcium or placebo are normal. Well, when we look at these comparative box plots, we can see that we don't have any evidence in our experimental group, the calcium group, of strong skewness or any outliers. And likewise in our placebo group, when we plot that sample data, we don't see strong skewness or any outliers. The graphs don't show those, so we're safe using two-sample t procedures. Now from the data, we calculate some summary statistics. For our calcium group, our sample size was 10. The mean decrease was 5 millimeters, with a standard deviation of 8.7 millimeters. And for our placebo group, our sample size was 11. We actually had a mean increase, or in other words, a mean decrease of negative 0.273 millimeters, and a standard deviation of about 5.9 millimeters. To calculate our test statistic, we use our T formula, and we get a test statistic in this case of 1.604. Now, by the conservative method, using the smaller of our two sample sizes, we'll use 9 degrees of freedom. Because the alternative counts only positive values of t as evidence against the null, the p-value is the area to the right of our test statistic 1.604 within that t distribution with 9 degrees of freedom. Now, if we look that up in Table B, we can find that the p-value lies somewhere between 0.05 and 0.10. If we were to use technology, using a two-sample t-test, we get t equals 1.60, and we get a p-value of 0.0644, using the actual degrees of freedom, in this case, 15.59. Now, if you're going to use technology to do the problem, you want to make sure you indicate the test statistic, the p-value, and the degrees of freedom when you give all of your evidence for the test. Now, because our p-value here is greater than our 5% significance level, we fail to reject the null hypothesis. The experiment does not provide convincing evidence that the true mean decrease in systolic blood pressure is higher for men like those who take calcium than for men like those who take a placebo. Now, assuming that the null were true, there's a 0.0644 probability of getting a difference in mean blood pressure reduction for the two groups of 5.273 or greater, just by the chance involved in the random assignment.
Alright, so hopefully that helped you get things squared away and your big ideas under control there with understanding what to do with your state plan to conclude. Again, your significance level, if it's unknown, just how this problem we worked on, again, it's always going to be 5%. Looking at your plan part, a lot of people are having issues with this. The plan part, go ahead and make sure to name the procedure. Two-sample t-test for difference in means. Talk about your conditions, write them out, your random samples, your 10% condition. And in this case, they're used essential limit theorem because we're dealing with means. List out those for each sample, not just one, for each one. And then dealing with the do part, make sure to figure out your standard error, in which case taking square root of your S1 squared over your sample size 1 plus your S2 squared over your second sample size. And then make sure to draw, very important, draw out your approximately normal curve, label it, do your shading so you can show where you're talking about getting your p-value from. Also too, when you're doing your p-value, if you have a calculator going this way, make sure to label each point, lower bound, upper bound, or degrees freedom. Or if you're using the table, write out table D and the p-value. It gives you between whatever two values it gives you. You need to label those so I can understand where you're getting your numbers from. And your conclusion, saying what is happening here, assuming there's no difference. Either it's between whatever, talking about the context, and then talking about the probability that you got of getting a difference of whatever the context is talking about, purely by chance, and then stating whether you reject or you fail to reject the null hypothesis. Alright, so it makes a lot more sense on the big ideas. I'll see you next time.